In this video, we will introduce a different way of looking at a first order differential equation, one that doesn't require us to go through um, the process of finding the solution, whether it's implicit or explicit, right? So if let's just, make a little list of what we've done so far. So as far as techniques for solving a first order differential equation, well, we've used the separation of variables, right? So when your dE is separable, then we have a procedure for that. If the differential equation is linear, then we have a method for that. And then we have some equations that are neither separable nor linear, but we have solutions that we can obtain by certain substitutions, right? So solving via substitutions, right? And as we've seen, there's a bit of algebra and a bit of calculus that goes into it. But at the end of the day, what do we end up with, right? We end up with either an implicit or explicit solution, right? So assuming we have a dependent variable of y and an independent variable of x, we might end up with something like this, right? Which would be the explicit. So maybe I should write it so that it aligns with the wording that I have above. So implicit would look, basically of this form, or explicit would be of this form, right? So again, it takes a lot of work to get to this point. So these techniques are just examples of techniques that we refer to as an analytic way of analyzing differential equations. So these are all analytic methods. And analytic in math usually implies something to do with calculus, right? So so the fact that we have to rely on derivatives and antiderivatives, you know, in conjunction with a lot of algebra just to get to these, one of these forms, then that's what we refer to as an analytic method, right? And they are important, right? But equally important is analyzing a differential equation qualitatively. Like, so what if the information that we want, so for instance, think of what sort of information we could get from having one of these equations, right? We could find points, we could graph the function for one, right? And a graph tells a lot about a relationship between two variables. We could find things like whether the function is increasing or decreasing, whether the function is concave up or concave down. We could talk about limits of the function, like what happens to the y as x gets arbitrarily large. So if those are the types of questions that we have, we may not actually need to find either the explicit or the implicit solutions, right? So there are certain questions we can answer without having to find these equations, right? So there are certain properties of the solution to a dE, right? Properties of a solution to a differential equation that can be obtained, or I should say, maybe these properties could be understood right, without the need for these analytic methods, right? So without using analytic methods, right? And some of these properties are like the ones I just stated. Like is the function increasing at a particular point? Is it concave up? Um, does it have a relative min and relative max, right? Or just simply, what does the graph of the solution look like, right? Those are things, believe it or not, we will be able to answer without having to solve explicitly or implicitly for the solution. All right. So let me just kind of use this particular example to give you an idea of what we can do. All right. So let's consider this differential equation. And let's say it's written already in the normal form. So let's say it's 3x squared minus 4y cubed, right? And now if we look at it, actually this is one that we could not use any of our methods to solve. It's not separable. It's not linear for sure, because we see our y to the third power. It doesn't fit the pattern for any of our substitutions, right? So this is a good example of saying, okay, we couldn't use any of our analytic methods to come up with a solution, but we can still answer questions about possible solutions of this differential equation. So for instance, if y of x is a solution to this differential equation, so is a solution which passes through, so let's say we know that it passes through a particular point, so which passes through the point, let's say -1, -2, right? I could figure out at this point if the solution is increasing or decreasing. Is it going up or is it going down? Well, how could I do that? Well, think about it. I know the derivative. The derivative is the key to that bit of information. From our work in calculus, we know that if our first derivative at a particular point is positive, then it means the function, whatever that function is, has to be increasing. And similarly, if the first derivative at a particular point is negative, then I know the function, whatever that function might be, it would have to be decreasing at that particular point. So if I wanted to know, so here's one question I could ask. Is y of x increasing or decreasing at this point, right? So increasing or decreasing at -1, -2. I don't need to find y of x to answer this because I already have the derivative. That's what the first order differential equation is defined by. It's the fact that the derivative is 3x squared minus 4y cubed. So all I would have to do to answer this particular question is take my derivative and evaluate it at this point, right? And then see if I get a positive number or a negative number. So let's see what we end up with. So we have 3 times -1 squared minus 4 times -2 cubed. So this gives me a +3 minus, and then this is that's that -8 times 4, so a -32. So we end up with a +35. So because this derivative, right, evaluated at -1, -2, turns out to be a positive number, then it means that this, whatever the solution is, I have no idea what the solution is. I really don't. But the solution to this differential equation has to be increasing at that point, right? So therefore, y of x is increasing. Now remember, increasing and decreasing, these are referred to as local properties. So at a different point, if the same solution were to pass through a different point, it might not be decreasing there or increasing there, right? But so these are what we call local properties. So at a specific point or over a certain interval. It doesn't mean for all values of x or for over the entire real line, for instance. It's just saying locally what is going on, right? So we can't just stop and say y of x is increasing, because that would imply it's always increasing. No, it's increasing, we know, at this particular point, right? Could be more, but we just don't have enough information, right? So with this fact, so for instance, if I were then to say, try to sketch the graph of y of x as it passes through this particular point. So just like a little snapshot. So the fact that it's increasing, it means it could go like this, or it could go like that, right? It has to be one of those two, right? So these are possible graphs of our solution at this particular point. So I'm not really going to label it, but let's just say that's the point -1, -2. So the graph of y of x could look like this, right? But how could we narrow it down? How could we eliminate one of these? Because it can't be both, right? We're talking about a single graph passing through a single point, right? Well, the difference between this type of graph and this type of graph now has to do with concavity, right? So for instance, this one right here, the graph is increasing and concave up, whereas this one is increasing and concave down. So if I had a way of, again, based on the information that's given, and all I have is the differential equation, and you can call this your initial condition. In fact, it is an initial condition, right? If there's a way I could then figure out, is the solution concave up or concave down, then I can eliminate one of these and say, yep, it has to look like this, or it has to look like this. Well, what do we know about concavity? Well, I always refer to a nice analogy like what the first derivative is to increase or decrease, the second derivative is to concavity. So if I want to know more about the concavity of a function, then I have to look at the second derivative. So it's almost like I need to turn this first order differential equation into a second order differential equation. Scary, right? But let's see how it works, right? And so what do we know about, so let me restate it. So dy dx is 3x squared minus 4y cubed. Well, if I were to differentiate this with respect to x, right? Because that's what I would have to do to find the second derivative. So differentiating with respect to x. Now, this is what it would look like. So I would take the derivative of my dy dx, and that's how I get that other Leibniz notation. And then over here, I would have to take the derivative of my 3x squared, which is not a problem. But here we have to be careful, because remember, y is dependent on x. There's that concept again. So what I'm actually differentiating is this: 4 times y of x to the third power, right? So I'll have to remember to use my chain rule here, right? Because what I have is, again, because of the dependency of y on x, then I have to remember so this term here, or I should say this factor here, is interpreted as y of x, right? Because y depends on x, but then it's raised to the third power. And because of my composite here now, I'll have to use my chain rule when I go to do my derivative, right? All right, so let's see what the second derivative comes out to be. So d2y dx squared. This part is pretty standard. That becomes 6x. And then here, this is where we have to be careful now. So the constant comes down. We have our 4. And then, thinking of it like this, apply the chain rule, bring the 3 down, keep the y of x, the so-called inner function. Not my favorite phrase, but it works. And then we multiply by the derivative of the inner function. But when I differentiate y, I get dy dx. So look at that. I now have a second order differential equation, right? Because there's a second derivative, here's a first derivative, and here's some other terms. So let's rewrite it in a simpler way. All right, so you got 6x, then this is minus 12, and then I'll just go back to the y with the x of x's being implied here, and then squared, and then I have my dy dx. Now, so we were able to write for the first derivative, right, the first order differential equation, in the normal form, we had the derivative on one side, and then we had our dependent and independent variables on the other side. Over here, not only do we have the independent and dependent variables, but we also have the first derivative. But it turns out I could do a little bit of algebra to get the second derivative to look a lot like the first derivative. In other words, since I know what dy dx is, dy dx is this expression, right? Why don't I take that expression and just put it there? And then I can get the second derivative solely in terms of x and y. So instead of it being, kind of dependent on the first derivative, maybe I could just express the second derivative only in terms of x and y, right? So get it to look like this. It's not going to be identical, right? But it will be of a similar form. So what we're going to do is for the dy dx, we're going to plug in that 3x squared minus 4y cubed that was given to us for our first derivative, right? So this is what our second derivative looks like. And then we have 6x minus 12y squared, and then put the quantity 3x squared minus 4y cubed. And then let's distribute what we can and, simplify it, right? So our second derivative is equal to 6x, and then so distributing the negative 12 y squared, we'll get negative 36. I'll put the x squared and then the y squared, and then distributing again the negative 12y squared to this term gives me a positive 48 y to the fifth when I add those exponents. So I have y to the fifth there. So this now gives me the second derivative in terms of x and y alone. So now that I have this, if I then wanted to figure out if my solution, right, is concave up or concave down at that same point, which was our, I believe, was 1 negative, let's go back up here and see what we have. Yeah, so it was 1 negative 2, negative 1 negative 2. And we've gotten to this point where we've narrowed it down to the fact that it is increasing, but we want to figure out, does it have this kind of shape? Is it concave upward, or is it concave downward? So now that we have the second derivative, we could say at -1, -2, let's see if our second derivative is positive or negative, because that's what determines concavity. So we have our ordered pair there, and then we plug in and evaluate. So let's see what we have. So this will give us -6, and then here we're going to have -36 times 1 times 4, and then plus 48 times -2 to the 5th power, right? Now, I don't have to do a lot here to figure this out. So for instance, this is -6, and then this is minus 144, and then this is a pretty big negative number, because -2 to the 5th power is -32, and then times a positive 48. So this is going to be -32 times 48. I don't need to get the specific number. The actual numerical value is irrelevant, right? Now, if I'm going to write it down, I would have to write it down correctly. But for me to determine whether the solution to this differential equation is concave up or concave down at a particular point, I just have to observe that the second derivative is negative. And whenever your second derivative is negative, that tells me that the graph of the solution has to be concave down at this point, right? So let's see what we have so far. So we can say that, in fact, so at -1, -2, y of x is increasing and concave downward. Right? So what that means is the graph of this solution has to look like this at that point. So at the point -1, -2, this is what the graph of the solution would have to look like. I have no idea what the equation is, and it's probably a very complicated equation, but just by using the first and second derivatives, we were able to identify these sort of qualitative properties that the function has, and that gives us an idea of what it's doing, right? So really powerful approach, right? Now, they always say pictures are worth 1,000 words, and in math, it's probably more like 10,000 words. It's worth a lot. Well, it turns out we can get a pretty detailed sketch of these solutions, again, just by using, in fact, we don't even need the second derivative to do what we're about to do, right? But there are two standard, like, qualitative graphs that can be produced for solutions of first order differential equations, right? So the graph of a solution to a first order DE may be produced as follows, right? The first one that we're going to look at uses the same idea of increase or decrease, and the type of graph or plot that is produced here is called either a slope field or a direction field. So a slope field or a direction field, right? It's a really simple idea. And what we do is, using the same concept of increase or decrease, right, we're going to actually essentially produce a whole set of little arrows that indicate whether the function is increasing or decreasing. So just to kind of give you an idea, not with a specific one, but just a general concept that's related to this. Let's say we have our differential equation in our normal form. And let's assume that f of xy, this function on this side, is defined for all values of x and all values of y. So we can plug different ordered pairs in, right, and get a number. And remember, that number, whether it's positive, negative, or zero, will tell me if the solution is increasing, decreasing, or neither, right? So to generate what we call a slope field, we evaluate our f of xy at a set of ordered pairs right? Observing, so let's say the ordered pairs are like x0, y0. So those are the ordered pairs. So we evaluate and then we simply observe whether f of x0, y0 is that positive? Is it negative? Or the only other possibility is it 0, right? If the function evaluates as something positive, which means our derivative is positive, what we do is we put a little arrow at that point in the xy plane pointing upwards, right? If the function evaluates to something negative, again, at that point in the xy plane, we're going to put an arrow going downwards, right? And then if the derivative or function evaluated at the ordered pair is neither positive nor negative, well, think about what this means. This is remember, when your derivative is 0, that's when you have a horizontal tangent line. So we put a little arrow like this. These arrows, right, simply indicate whether the solution is going up, right? So is it increasing, is it decreasing, or is it constant, right? And these arrows are referred to, they're called lineal elements. So they're not like lines, because lines extend indefinitely, right, in multiple directions. These lineal elements are basically little directed line segments that indicate the slope of the solution at a particular point. And the set of all of these lineal elements is what we refer to as a slope field. Right? So a slope field is a set of these lineal elements. And again, it allows us to paint a picture of what the solution does, right? So lineal elements. And that's our slope field. It gives us a visual of what it does, right? And so I'm just going to end this video with just a little, like me just making up a slope field. In the next video, I'll have an actual slope field that's generated by software, and we can talk about how to use something like that. But basically, let's say, and here I'll give you a specific one. Let's say we have x minus 2y as our differential equation. Now, this is something we could solve, right? This is something we could solve. we could write this in the standard form and use our integrating factors, and we could get in fact we could get an explicit solution. It looks like we would probably have to use integration by parts, but that's not what we're doing now, right? We're looking at this in a different way, answering questions that are more qualitative than they are analytic. So let's say I'm going to pick points in the each of one in each of the four quadrants, right? I'm just going to make a table. So I'm going to refer to, so this will be my x0, this will be my y0, and then I am just going to evaluate the derivative, right, my function here, at each of those ordered pairs. And then just see if we get something positive, negative, what sort of numbers we get, and then I'll show you what the lineal elements would look like. But in practice, this is not something you do by hand. You use software like MATLAB or Maple, or in fact, there are lots of online things that can generate slope fields for you. But let's say, so in the first quadrant, let's say I use the point 1, 2. So if I plug 1 in for x and 2 in for y, I will have 1 minus 4, so that's negative 3. And what this means is, at the point 1 comma 2, because the slope, right, is negative 3, then I would have to have an arrow. So let's say, and usually what we do is we have the arrow kind of going through. It doesn't start at the point, but it's kind of at the middle. I mean, I guess some software actually do have it starting at the particular point. And in this case, since the derivative comes out to be negative, our lineal element will be pointing downwards like this. And then the thing is, all the other lineal elements that we sketch would be relative to this. So for instance, if we had a slope of negative 1, then it wouldn't be sloping as steeply downward as this one, right? Let's pick a point in the second quadrant. So let's say negative 2, 1, right? So if we're over here, so at this particular point, if I plug negative 2 in, then I'll have negative 2 and then minus 2, so negative 4. So this one at this point would also be sloping downwards, right? But it would have to be steeper than this, so probably like that, right? Because again, this is, in terms of a rate of decrease, right? This one is decreasing more rapidly than this one, right? Let's see, in the third quadrant, and they're both x and y would have to be negative. So let's say I pick negative 1, plugging that in there, I would have negative 1 plus 2. So now that's a positive 1. So at the point negative 1, roughly here, it'd have to be sloping upwards, right? And maybe something like that, right? And then finally, let's pick a point over here. So let's say 3, negative 2. So like this. So roughly that point. If I plug 3, negative 2 into my derivative, I will end up with 3 plus 4. So that's 7. So much steeper than this. I mean, it would almost have to be almost vertical, right? Sloping upwards. But again, you do a whole set of these, and it's like you have a whole collection of arrows, and those arrows are telling me where all the solutions to the differential equations, where they would have to be going. Are they decreasing? Are they increasing? And if so, are they increasing more rapidly at this point versus this point, right? And with that, we can generate a pretty detailed sketch of not just one, but actually several solutions to this differential equation without ever having to do an integral, right? And again, it's not, I don't want to put down the analytic methods. They're extremely important and they serve, you know, lots of good purposes. But just depending on what you specifically need, you might be able to answer your question without having to go through the process of those analytic techniques, right? And here we just kind of touched on the surface, and in the next few videos we'll go a little bit more deeply into what we can do qualitatively. So if you're interested, why don't you hop on over to the next video? I'll see you then.